This is our second video for Unit 3, and it's on equilibrium. So be sure to open your packet to the notes page, take some notes, and you'll be able to use them on the video quiz at the end. What I want you to be able to do when you're done with this video is to explain the difference between mass and weight. Then I want you to be able to tell me the equilibrium rule. And finally, we're going to talk about different types of equilibrium in physics: mechanical equilibrium, static equilibrium, and dynamic equilibrium. You'll put this knowledge to use right away with two problem sets in your packet. So let's get started. First, I want to talk about the difference between mass and weight. A lot of us use these two terms interchangeably, but there is a difference. And let's talk about that now. Mass refers to how much stuff, or in physics and chemistry we call this matter, is in an object. If you're talking about the mass of something, you'd use the units of grams. For example, a nickel has a mass of 5 grams. The weight of something is actually the force of gravity pulling down on that mass. So weight is a force, and mass is the amount of stuff that something has. The metric unit for weight is newtons. So if something had a weight, it could be 5 newtons. Now remember, we said that a newton is about 1/4 of a pound on Earth. So if something weighed about 1 pound and 1/4, that would have a weight of 5 newtons. I think the best way to understand the difference between mass and weight is to look at an example of how mass and weight can change or not. One kind of classic situation is comparing how the mass and weight of something differ on the Earth and on the Moon. So remember, weight was the force, and it was the pull of gravity on how much stuff or mass was in something. This graphic uses a bag of flour that's 2.3 kgs. And we would recognize that as being a 5-pound bag of flour. So like your regular standard size bag of flour. So on Earth, a 2.3 kg bag of flour is going to have a weight of 5 pounds because gravity is going to be pulling that flour down. 5 pounds is 22.2 newtons. Now let's suppose we move that bag of flour to the Moon. Its mass is still going to be 2.3 kg because the amount of flour in there is the same. Now what's going to be different is that the pull of gravity is less on the Moon because the Moon is smaller than the Earth. So what happens is that pull of gravity on that 2.3 kgs is less, so the weight is only 0.8 pounds on the Moon, or about 3.6 newtons. So compared to the Earth, your weight on the Moon would only be about 1/5 of what it is on the Earth. We'll get into the difference between mass and weight a little bit more in another unit, but since we're talking about forces now, and one of the forces we're talking about is gravitational force, I figured now would be a good time to introduce it. Now I want to talk about another concept, and that's the concept of net force. What's net force? The definition of net force is the sum of forces, all of the forces acting on an object. Now you can write net force in some different ways. One way to write net force is F subscript net or F subscript sum, just like we've been writing abbreviations for all the different types of forces so far. And another way you can write this is sigma F. It looks kind of like a letter E, and then you'd write F. Either one of these is a way to represent net force. You're probably going to run into the Greek letter sigma if you study more math or science, and it just means the sum of something. The reason we want to talk about net force is because net force is really handy to talk about objects that are in equilibrium. The first type of equilibrium that we're going to talk about is called mechanical equilibrium. And what that means is it's a state where there are no physical changes to an object. The physical changes that we're going to be most concerned about is speeding up or slowing down in their motion or changing directions in their motion. Now, there are two different types of mechanical equilibrium, but before we get into that, I want to talk about something called the equilibrium rule. So, the equilibrium rule says that in order for an object to be in equilibrium, the net force on it has to be 0. So when an object has a net force of 0 newtons, it's going to be in mechanical equilibrium. Now that doesn't mean that there's no forces on the object, it just means that the forces are in balance. And we'll look at some examples in just a minute, so if you're feeling a little bit confused, it's okay. For right now, I want you to know that the equilibrium rule says that the net force on an object is 0, and that can be expressed in words like it is up here, or as an equation, just like it is down here. So this equation, if you remember, net force, or the sum of all forces, equals 0 newtons. There are two types of mechanical equilibrium, static equilibrium and dynamic equilibrium, and we're going to talk about those right now. So in order for an object to be in equilibrium, remember, the sum of all forces on it have to be 0 newtons. Now for an object to be in static equilibrium, that means that the object isn't moving. So that's a key. In order to move an object, you'd have to apply a force to it. Then the net force would not be 0 newtons and the object wouldn't be in equilibrium. Let's look at this example. The example of static equilibrium shown here is just a man standing still, a stationary person. Now there are forces acting on this person, and one is right here. That's their weight, or the force of gravity pulling down on them. Now you remember that since this person is standing on the ground, that ground is going to be exerting an upward force on them, and that force is called the normal force. So there are two forces acting on this guy just standing there, but they're equal and opposite. They cancel each other out and make it so that the sum of forces is 0 newtons. This guy's in equilibrium, and since he's standing still, he's in static equilibrium. Let's look at a situation where an object is in dynamic equilibrium. So remember, equilibrium means that the sum of all forces is 0 newtons, and dynamic equilibrium is just a situation where the object is actually moving. But an object can't just be moving in any way. There are two characteristics of how the object has to be moving to be in dynamic equilibrium. The object has to be moving at a constant speed, so not accelerating or decelerating, and the object has to be moving in a straight line. So it can't be moving in a circle or changing directions. In this example, if the car changed its speed or its direction, now this car wouldn't be in dynamic equilibrium anymore because there would be a net force. Now this is a little bit confusing to imagine how the net force on a moving car is 0 newtons. So let's look at this force diagram and kind of dissect it. Here you have the biggest force at play, and that's the force of gravity, or the weight pulling the car down to the road. Since the car's tires are being supported by the road, you have normal forces at each of the tires. The push up from these normal forces combined together is equal to the push down from gravity, or the pull down from gravity, I should say. Now there's an applied force from the engine, from the motor, pushing the car forward. But that's balanced by this force pushing the car back, and that's going to be the force of friction. So what you have here is all of these forces canceling each other out, but still the car is moving. Since all the forces cancel each other out, the net force is 0 newtons. Since the object is moving, it's in dynamic equilibrium. Let's look at a couple of problems, examples of what you might see on your problem set. So, knowing our equilibrium rule, that the sum of all forces equals 0 newtons, we can approach a problem like this. What we have is a block hanging from two strings. Since the sum of all forces is 0, any force that's pulling this block down has to be balanced by forces that are pulling the block up. In this case, we see that the force of gravity is 200 newtons. That's the force that's down. This means that the force up has to also be 200 newtons. Since the block is supported by two ropes, those two ropes are going to equally support the block, which means that each of those ropes is going to have a tension force of 100 newtons on it. Do you see how this works? If we add up these force vectors, we have a vector for 200 newtons pointing down and two vectors for 100 newtons pointing up, and those vectors will cancel each other out. So you'll see problems like this where you'll have to fill in blanks of objects that are in equilibrium. Let's look at this final example. What we see is a board that's being supported by two ropes on either side. On the board, there's some type of brick or object. We can see that gravity is pulling this brick down with a force of 180 newtons, and we can see that the board is being pulled down by gravity with a force of 180 newtons. Now, altogether, the weight of these two objects is going to be 320 newtons. Since this is in equilibrium, that means that the forces pointing up have to be also equal to 320 newtons. We see that over here, the tension force in this rope is 200 newtons. But we don't know the tension force in this rope. Since this object is in equilibrium, we know that the sum of all the forces have to equal 0 newtons. So, we could kind of set it up like this. What are all of the forces? Well, we have this force of gravity equaling 140 newtons. This force of gravity equal 180 newtons. In the opposite direction, we have a tension force of 200 newtons, and we don't know the other tension force. Altogether, those have to add up to 0. So let's combine the like terms. Here we have 320 minus 200. That would equal 120 newtons. Minus x equals 0. We can flip the x over to the other side to make it positive, and then we'd have x equals 120 newtons. If we write that in here, we see that these up tension forces combine together to equal 320 newtons, and that equals the downward force of gravity. Go ahead and try the problem sets after you take the video quiz. If you're having difficulty, be sure to ask a question or watch this video again.